Moving on to another example with all of these thermodynamics calculations. We're going to look at the reaction where ethine, so we've got 3 moles of gaseous, can't say that word today, ethine, are going to polymerize to form benzene. Okay, now don't worry too much if you put an equilibrium arrow there or not. You'll see that a lot more as we get into some of these problems. We're asked to calculate a number of things. First of all, the entropy change, then the enthalpy change, and then we're asked to talk about spontaneity, and then also optimum conditions for the formation of benzene. So I want you to pause the video in just a minute and figure out the entropy change and the enthalpy change on your own. So you're going to calculate the delta H of reaction. You're given heats of formation. So you're going to go ahead and use the formula where you add up all of the heats of formation of the products and subtract all of the heats of formation of the reactants. And then, oops, except that I just messed up the enthalpy versus entropy thing here, so hang on. All right, so, and this will be of the reactants. So that would actually be for B, right? So that goes with this one. And then for the entropy, you'll do the same thing with the entropies that are given. So it'll be entropies of the products minus entropies of the reactants. Okay, so pause the video now and go ahead and get those calculations done. All right, so now that you've had a chance to calculate those, for the entropy, you should have gotten negative 334 joules per Kelvin. I converted this to kilojoules because I know I'm going to need to do that when we start to look at the spontaneity piece of this, because it's going to need to be in the same units as the delta H to do those calculations. So for your delta H, for your enthalpy of reaction, you should have gotten negative 598. Now, if you didn't get that, pause the video for a minute, take a look at my work, see if you can figure out what went wrong. And now I'm going to proceed on to part C, which asks me about the spontaneity of this reaction. So the thing that relates these two things into spontaneity is this equation right here. So if delta H is negative 598 kilojoules, we're trying to calculate the delta G. The temperature for all of these is 298 Kelvin because, pardon me, that should be a 9. Remember that all of these values are at standard conditions. That's what this little knot symbol means. So, and standard conditions are 25 degrees Celsius, which is 298 Kelvin. So I've got 298 Kelvin times negative 0.334 kilojoules per Kelvin, and I get negative 498 kilojoules for that. So then the last part of this question is predict the optimum conditions for the formation of benzene. So this is a situation where at 298 Kelvin, our entropy change is negative and our delta H, our enthalpy change, is negative. Now, if you remember back to that chart we made in the previous video, when we have that situation, the negative entropy change and a negative enthalpy change, that is going to give us the situation where things will be spontaneous if it's below a certain temperature. So if we can calculate where delta G equals 0, okay, so that would be the point, below that temperature, it would be spontaneous. Above that temperature, it would be non-spontaneous because the delta G would be positive. So where delta G equals 0, that temperature is sort of the cutoff, so above that temperature, benzene won't be formed, or below that temperature, benzene will be favored. So basically, you would set up the equation delta H, this equation here, you would set that up, set delta G equals to 0 and solve for temperature. And when you do that, below that temperature, benzene will be favored. Okay? Or in other words, the forward reaction is spontaneous. Sorry, I'm having a little trouble with my pen there. I'll write it down here. Okay, and we'll look at some more where we actually do that calculation. All right, that was just some more space, and now onto this slide. So there's another way that we can determine delta G of reaction, and that's to use a very similar concept to the heats of formation, and these are the Gibbs free energy of formation. That can be looked up again in the data booklet or in the ZoomDall, or sometimes it's given in the problem. But again, it's going to be products minus reactants. So here's an example we're going to work through where we're going to use all these different values. So we're given Gibbs free energy of change of formation to start with, and we're going to try to figure out which is more stable at 25 degrees, the cis or trans isomer of but2ene. Now, you don't really need to know anything about organic chemistry to do this, but when you see these names, it's kind of overwhelming, I think. So basically what we're saying is there's two isomers of 2-butene. One is a cis isomer, one's a trans isomer, and that has to do with some arrangements around the double bond, and we'll go way into that in organic chemistry. But the point here is that this is the reaction you have. You have an equilibrium between the two isomers, and depending on the temperature, one of them is more stable. And we're going to figure out which one from this these thermodynamic calculations. Basically, if this reaction is spontaneous at 25 degrees Celsius, then the trans isomer will be the one that is more stable. If we find that it's not spontaneous, that means the cis isomer is favored, and so therefore the reaction is not spontaneous in that direction. So the cis isomer would be favored. Okay, so let's look at how we would figure that out. So to figure out the delta G of the reaction, I'm going to use that formula we just had on the last slide. So I'm going to add up all of my delta G's of formation of my products and subtract all of the delta G's of formation of my reactants. Sorry, having a little trouble with my parentheses there. Okay, so let's go ahead and do the math. So it's a 1-to-1 ratio, so I'm multiplying everything by 1 mole. So if my trans is my product, then 64.1 kilojoules minus 67.1 kilojoules will give me negative 3.0 kilojoules. So if that delta G is negative, that means this process is spontaneous. So that means that the trans isomer is more stable at 25 degrees Celsius. And then the second part of the question is a little more complicated, and I'm going to move to a different page that has a little more space to work on this. So now it's asking us, what temperature will the two isomers have the same stability? So in other words, the spontaneity of the forward reaction would be equal to the spontaneity of the reverse reaction. This point where they have the same stability, that would be when delta G is equal to 0. And so we're going to need to do some more calculations in order to be able to do that calculation. And I'd like you to try to do as much of it as you can on your own before you, I'm going to have you pause in a minute and have you come back. So you're going to need to calculate the delta H of reaction. We're going to do it the same way we did it for the previous problem. I also want you to calculate the delta S of the reaction. And then I want you to use this formula. Delta G is going to be equal to 0. You're going to substitute in the delta H from up here. You're going to substitute in the delta S from up down here. All right, so you're going to have your delta H from up here, your delta S from up here, and then you're going to solve for temperature. Okay, so I would like you to pause the video now, work through all of that, do as much as you possibly can, and then come back and take a look at my work. All right, so coming back to looking at the work and how to do this problem, hopefully you were able to certainly do the delta H and delta S part of things, since you're just doing the products minus reactants. And then when you get to solving for delta G, you're going to use the delta H from here, the delta S from here, and then you solve for T, because the point at which these two things will be equally stable is when delta G equals 0, because that's the point where delta G isn't negative or positive, so it's not more spontaneous in one direction than another. And when you solve for temperature, you get 880 Kelvin. So at 880 Kelvin, the cis and trans isomers will have the same stability. Now, on the PowerPoint I've given you, there are 2 more problems. And I'm going to leave those for you to work through. I can certainly help you as needed. And I just wanted to end, of course, with a little chemistry joke for you. And there you go.